Hello everybody, and welcome to the beginning of section 1.3. In this section we are going to be talking about something called a subspace of a vector space. Let's start with a definition of this term. Okay, so let V be a vector space over F, and let W be a subset of V. We're going to call that subset a subspace if W itself is a vector space under our operations. Okay, let's draw a picture just so that we can kind of get a feel for what this is saying. So they're starting us off with something that we know as a vector space V, and we're taking a subset inside of V and calling it W, and we're going to call that subset a subspace if W itself is also a vector space, if it has all of the properties of a vector space. Okay, so a subspace is just a smaller vector space inside of something that we already know as a vector space. Okay, so let's do an example where we show that something is a subspace. They'd like us to investigate whether or not W, which is the set of all ordered pairs that have the form A3A, is a subspace of R2. Okay, so to kind of use the notation of the definition, we'll call R2 V. That's our big vector space. We already know that that's a vector space. We'd like to show that this subset of V is also a vector space. Well, how do we do that? We have a definition of what it means to be a vector space. I'm going to flip pages on you here and take you back to section 1.2 where we defined a vector space. Okay, so to prove that W is a subspace, we would technically have to go down this list and prove that W has all of these properties. Okay, now that would take a long time if we really had to do that for every item on this list, so it turns out that there's kind of a shortcut here. Okay, so to investigate that, I'm going to just redraw the picture that we drew on the previous page. Okay, so we had our big vector space, V, okay, which in our case was R2, and then the W that lived inside of it. Okay, and we're trying to show, again, that the W is a vector space. We already know that the V is a vector space. Okay, and to illustrate the point here that I'd like to make, let's pick on one of the items on this list, VS1. Okay, that statement, as it's written, is true. For all x, y, and v, x plus y equals y plus x. How do we know that? Well, we know that because R2 is a vector space. Okay, we already know that. The question we're asking is, would VS1 also be true for W? If we took the V and replaced it with W, would that be a true statement? Well, if you think about it, it has to be, because if the statement VS1 is true for every vector in R2, it's certainly got to be true for every vector in W, because W is a smaller set. Okay, and there are other statements on our list that have that general form. VS2, for example. That's a statement that's true for every vector in V, and so it's certainly going to be true for every vector in W as well. And we could go down the list and find other statements that have that same general form. 5, 6, 7, and 8 we can make similar statements about. So VS1, 2, and 5 through 8 are true by default. Okay, we're going to use the word, those properties are inherited from V. So really, all we have to prove are those things, closure, and then VS3 and VS4. Okay, so back to the previous page, let's see if we can do that. All right, so let's start with the observation that we made from the previous page that some of the properties on the list of a vector space are inherited. So properties VS1, VS2, and VS5 through 8 are all inherited from V. We don't have to show those, okay, because they're already true in V. So what we do have to check are the other ones. Okay, so we made this remark on the previous page, closure, VS3, and VS4. All right, and let's start with closure. So we need to take two vectors that are in our vector space. So take any x and y. And here let's remind ourselves what our vector space looks like. So to be in W, our vector has to have the form a and 3a. In other words, the second component has to be 3 times the first component. So we'll take two arbitrary vectors that have that form, x equals a 3a and y equals b 3b. Okay, and any scalar in R. Okay, then we start with vector addition. We'd like to show that x plus y is in W. Okay, oh, and actually, let me fix one thing here. I really should point out that the x and the y that we chose are in W. Okay, just to make this correct when I'm writing. Okay, so we chose our x and our y in W. Now we want to look at x plus y and convince ourselves that that's in W. Okay, so x plus y looks like a 3a plus b 3b. If we add those together, we get a plus b and 3a plus 3b. Okay, now how sure are we that that ordered pair is in W? Well, to be in W, we have to prove that the second coordinate is 3 times the first coordinate. We can do that by noticing that a 3 kind of naturally factors out of the second coordinate. Notice that by doing that, we can look at this ordered pair and see, oh, yeah, the second component is 3 times the first component, and that's exactly what it means to be in W, so we can say with confidence that that's in W. Okay, now what about closure under scalar multiplication? Well, we want to take a scalar c and multiply it by one of our vectors. So that would be c times a and 3a. If we do that multiplication, we're going to get ca and c times 3a. And again, we're asking the question, does that ordered pair fit this general form? It does, and we can point that out by noting that that second coordinate can be written as 3 times the first coordinate. Okay, and that's what it means to be in W. Okay, so we have just proven that W is closed under addition and scalar multiplication. Okay, good. So we have just crossed closure off of our list. Next thing that we'd like to look at is VS3. Okay, and VS3, if you peeked on back in the workbook, VS3 is the statement that the 0 vector is in our vector space. So we'd like to show that the 0 vector, which in the case of R2 looks like 0, 0, is in W. Okay, well, again, how do we get in W? We need to show that that vector can be written in the form a and 3a. Notice that it can, because 0, 0 is equal to 0 and 3 times 0. So it does indeed have the form of being in W. Okay, so we've just proven VS3. And last thing we need to look at then is VS4. Okay, now we could prove this directly, but there's kind of an observation that we can make here. Okay, so I'm going to erase this and just phrase this a little bit differently. Okay, so instead of doing VS4 directly, we're going to kind of make an observation here. So if we start with something that's in W, note that negative x, by something that we proved in a previous section, is equal to negative 1 times x. Okay, that was actually Theorem 1.2, so we know that that's true. And negative 1 times x, that's a scalar times a vector x that we know to be in W, and so that has to be in W because of the fact that we proved closure above. Okay, so since W is closed, so notice that what we just proved here is VS4. Okay, we started with x being in W, and we proved that negative x is in W. Okay, and we were able to do it using the stuff that we already proved. Okay, closure and VS3. So actually, we didn't need to prove VS4. It was implied by the two things that we already proved. So here's the comment that we're going to make. VS4 is implied by closure under scalar multiplication, which we already proved. Okay, so what that tells us then is that to show that something is a subspace, we really only need to do these two things, which I'm circling in green. We need to prove closure and the fact that the zero vector is in our vector space. Okay, and so what that brings us to is Theorem 1.3, one of the most important tools that we'll be using in our course. And it says that if W is a vector space and W is a subset of V, then to show that W is a subspace, all we need to do is to prove these three things, that the zero vector is in our set, that's VS3, and then closure. And in upcoming videos, we'll demonstrate how we can use that, okay, to prove that subsets are subspaces.